Alright, hello everyone. We're back for another video. This one is on the mole. Alright, it's a very important concept in chemistry, and it's a concept that is, while on the surface very simple, is always very hard to understand and conceptualize. The problem is atoms are very tiny, and so we can never really deal with one atom or two atoms. We always deal with basically trillions of atoms. And so we end up using the mole as kind of a generic amount, all right? Or 602 billion trillion atoms is one mole. So it's just an amount. It's like saying instead of working with in one egg, we're going to be working with dozens of eggs. So, you know, we'll bake a cake with 3 dozen eggs or 4 dozen eggs. This is kind of the same concept. We'll be reacting not one atom or 2 atoms, but 1 mole or 2 moles or 3 moles. Just to kind of get a scale, a mole is about 12 grams of carbon, so for a lot of your elements it'll fit in the palm of your hand. So it's just a nice amount to work with. It's not a ton, it's not a little bit, it's a mole. And the way they came up with this is essentially they put hydrogen at 1. They say, okay, we'll make hydrogen, a mole's worth of hydrogen, 1 gram. Okay, because hydrogen is the first element, so we'll say it's 1 gram. And then we'll scale it up from there. And so that's kind of how it worked. So yeah. Okay, so what we do is we use the mole to balance a chemical equation. Now, matter can neither be created nor destroyed. It has to be conserved in a chemical equation. So we're not dealing with crazy, weird physics where matter turns into energy and all that. We're just going to deal with regular old chemistry. We cannot create or destroy matter, therefore we have to balance equations. So I have this sample equation. It's hydrogen gas plus oxygen gas yields water. Alright, this is a fun little equation. These little double arrows, you probably have never seen them before. Let me blow them up over here. It actually looks like this. They're actually 2 half arrows. And this means that the reaction could proceed from left to right, but it could also proceed from right to left. It's a reversible reaction. Right now, we're just going to get in the habit of drawing those instead of the regular old one-way arrow. So we're just going to draw these double arrows and really not worry about what they mean or the impact of the double arrows until next semester when we start dealing with reversible reactions and equilibriums. Okay, so I have this reaction right here and I need to balance it. Very simply, we just pick an element. So I'm going to pick hydrogens. On this side, I have 2 hydrogens. On this side, I have 2 hydrogens, so my hydrogens are balanced. Right here, I've got 2 oxygens, but I only have 1 oxygen here. The way we balance our oxygens, we have to add coefficients. I just can't put a 2 here. If I were to put a 2 there, that turns that from water into hydrogen peroxide. Those are not nearly the same thing. Alright? We cannot put subscripts. We have to put big coefficients. This is saying I've got 2 waters. So I have 2 oxygens here, I have 2 oxygens here. The problem is, it also changed my hydrogen count. See that? Now I have 4 hydrogens. Well, I have to put a 2 there because 2 times 2 is 4. So 4 hydrogens, 2 oxygens, 2 oxygens. So that's a balanced reaction. These coefficients are not actually talking about the molecules. This isn't saying I have 2 molecules of water. It's actually saying I have 2 moles of water. So this reaction is really if 2 moles of hydrogen and 1 mole of oxygen react together, they will yield 2 moles of water vapor gas, or water vapor. All right, so these are actually moles. A lot of times it's easier to think of them in terms of atoms. It's really kind of splitting hairs, but these are actually moles. They're not atoms. Okay, couple of things that are kind of important. I'm just going to toss them up here. AMU stands for atomic mass unit. That's the mass of 1 atom, an atomic mass. It is equal to the grams per mole. So, for example, hydrogen has an atomic mass unit of 1.01. It's either AMU for atomic mass unit if we're talking about 1 hydrogen. If we're talking about a mole's worth of hydrogen, it's the molar mass. And the unit for molar mass is a grams per mole. Okay, so it could be 1.01 AMUs or grams per mole. They're the same thing, just talking about different, whether it's in a single atom or a mole of them. Alright, and this is Avogadro's number, 6.02 times 10 to the 23rd. It's going to be very important. We're going to be dealing a lot with Avogadro's number. So you'll have it memorized. You won't have to memorize it, but you'll just have it memorized. Okie dokie. Let's talk about converting with the mole, because this is all fine and dandy, but it really doesn't do anything. I mean, it's fun knowing about moles and balancing and Avogadro's number. It's much more important that we can convert between moles and balance and use Avogadro's number. So let's talk about conversions. Okay. So the reason we have moles is it's kind of like a stepping stone. So if we think about moles, moles would kind of be in the middle. Right? And on one side of moles, we would have the mass of a substance. So let's say we have 5 grams of something. Moles would be in the middle, and atoms would be over here. Okay? Excuse me. Right? Now we can convert between atoms and moles, and we can convert between moles and grams. But we can never jump straight from atoms to grams. We can't do that. That's not possible. All right? That's impossible. Let me double line. X. Cannot do it. We have to go through moles, and that's why moles are important. All right? That's pretty much the only reason why moles are important. Because we don't think in moles. I don't like pour a bunch of carbon in my hand and go, oh, that's about half a mole of carbon. No, I don't think like, I think in grams. But moles are the bridge to get to atoms. And since things are happening on the atomic level, we need a way to bridge what we see with what's actually happening on the atomic level. So we have to bridge between our observations and the actual thing that's happening. And the bridge between observations and what's happening is the mole. That's why it's so important. The mole is the gateway between our observations and the science behind that. Okay? That's why the mole is important. And that's why we study the mole. And that's why we spend so much time on the mole. It is the mathematical way to get from mass to our actual atomic dealings. Alright? It's not a real bridge. It's an imaginary bridge. Okay? There's not a mole bridge. Just wanted you to be aware. Okay. So, let's actually talk about our conversions here. Okay, there's a couple of rules with conversion. And I kind of wrote them in the margins here. So, a couple of rules with conversion. Rule number 1. Same units must be diagonal. Oops. Got the A there. Same units must be diagonal from each other. Okay? That's rule number 1. Rule number 2. The top right unit appears in the answer. Okay? So, the top right unit will be the unit for the answer. So if our top right unit is not the unit we want, we're not done. We have to keep going with our conversion until we have the unit we want to appear in our answer. All right, if we know the unit we're looking for, we just start tossing stuff together until the unit we know we're looking for is on the top right. Right? There is no generic equation for this. That's the problem. There's no like, just wrote step 1, step 2, do this, plug these numbers in, get the right answer every time. No, you have to actually kind of interact with the numbers. You have to think about what you want and keep putting the same units on the diagonal until what I want is in the top right. It's like a puzzle. It's a puzzle for your mind. Now let's start easy. Let's say I have 2 moles of anything. And I want to know how many atoms that is. Okay? I have 2 moles of anything and I want to know how many atoms that is. Or how many atoms that is. Not are. Okay? Well, so I start with what I have. I have 2 moles. Okay, well that's great. Doesn't really help us too much, right? Well, there's a fun thing in math. I can put anything over 1. Doesn't change it, right? 2 over 1 is 2. I didn't change it, I just put it into a fraction form. Well, that helps us out because our conversions, we're going to be dealing with fractions. So 2 moles. times. Need another fraction. Okay. Well, I gotta look back here. All right. Well, the same unit must be diagonal. Okay. Well, that helps. So I know moles has to go down here. Okay. It's probably gonna be 1 mole. Okay. I'm looking for atoms. Well, I know Avogadro's number is 6.02 times 10 to the 23rd atoms in 1 mole. So it's 6.02 times 10 to the 23rd atoms in 1 mole. Now, think math-wise. Think about mathematically what we're doing here. I'm taking 2 and I put it over 1. That didn't change anything. And I'm essentially multiplying it by 1, right? Because 6.02 times 10 to the 23rd atoms is 1 mole. So these are the same thing, right? So 5 over 5 is essentially 1, right? The same thing over itself is 1. Well, 6.02 times 10 to the 23rd atoms is 1 mole. So it's over itself. I have 6.02 times 10 to the 23rd atoms over itself, and that's going to be 1. I'm multiplying this number essentially by 1. All I'm doing is changing the unit on it. I'm not changing the number. I'm changing the units, essentially. By changing the units, I guess I changed them. Okay, so I'm changing the numerical number, but I'm not changing the amount, I should say. Okay, well, let's do this out. Whenever I multiply fractions together, I multiply the top, multiply the bottom, and divide. Well, 2 times 6.02 times 10 to the 23rd atoms is going to be, I'm going to put it down here, because I don't know how much room I have over here. 2 times 6.02 is 12.04 times 10 to the 23rd. But that's not scientific notation. That's not scientific notation. I have to move the decimal over. So that really equals 1.204 times 10 to the 24th atoms. All right? We'll notice that our moles end up canceling out. So our unit is just atoms. Okay, so the quantity hasn't changed, just the unit and the number. But the quantity is still the same. This is exactly 2 moles. I haven't changed the quantity at all. I've just multiplied a number by 1, essentially. Okay, so mathematically we're really not changing a whole bunch of stuff. All right. Let's say I have 2 moles of water, and I want to know how many grams that is. I want to know how many grams 2 moles of water is. That's kind of important. Right, now we're dealing with actual amounts, right? I don't want a tank that can only hold 5 grams of water and need to cram 10 grams into it. That's not going to work out well. So, do the same thing I did over here. I take my 2 moles of water. Going to put it over 1. Didn't change anything. Did not change anything at all. I'm going to multiply it by, excuse me, a conversion factor. Now, the unit that has to go on the bottom is moles of water. I'm going to do 1 mole of water. Okay? On top. Now, what I want, ideally, is grams. And so I'm thinking, do I know how many grams 1 mole of water weighs? And I of course know. And you should know too, right? It's the molar mass. That's how many grams 1 mole of something weighs, is the molar mass, the mass of a mole. Right? The mass of a mole is my molar mass. I know my molar mass of water off the top of my head because I'm a nerd. Alright? And I'm proud of it. It's 18.02 grams. So, now the math's easy, right? Multiply my top numbers, multiply my bottom numbers, and divide. Okay? So I'm going to be left with, let me turn my back to you, I'm sorry for that, 36.04 grams. Notice I've got moles on the bottom, moles on the top, so those are going to cancel out. Oops, sorry. Of H2O. There you go. Okay? Problem solved. Now, right now, we're really not dealing with sig figs, okay? Right now, I'm really not dealing with sig figs because I'm introducing this topic. But But after I introduce this topic, we will be dealing with sig figs. Okay, so for all of you screaming out there, that's not correct, that should be 40, because I only have one sig fig. I'm aware, okay? So we'll be dealing with sig figs in a little bit, but I want to introduce one thing at a time. Okay, now let's take it one step harder. I'll take it one step harder. Now, if you'll remember, I had this drawing up here at the top, and you know what? I'm going to rewrite it just because I think it's a good drawing. Remember, we had atoms, and mole, and mass. I guess we could have volume up here too. Okay? Now, so far, we've been just kind of going one way, right? We've kind of just been dodging one way. But we can use the mole as a bridge, right? We don't have to stop with the mole. We can use it as a bridge. Let me say this one. Let's say I have 30 grams of O2. Well, how many atoms is that? How many atoms is 30 grams of O2? All right. Well, we start the same way we've always been starting. 30 grams of O2 over 1. All right, so what goes on the bottom? Well, grams of O2 go on the bottom, right? Okay, so grams of O2. What do I know about grams of O2? Well, I know there are 32 grams in a mole. Well, that'll help me out. 32 grams in a mole, I'll write that down. But notice, I don't want moles, right? I want atoms. So I just can't do this out and give an answer, because it's not going to give me the answer I want. This is where we have to keep going because we're not where we want to be yet. So, okay, I'll just slap on another line. Okay. Well, I have to put one mole down here. Okay, so 1 mole. 1 mole. Now, I want atoms. So I'm thinking about it. Well, I know how many atoms are in a mole, right? It's 6.02 times 10 to the 23rd. That's how many atoms are in a mole. Well, take a look. My grams of O2 are going to cancel out. My moles will cancel out. And I got the unit I want. So all I have to do is just start plugging and chugging into a calculator. Deep-donk, deep-donk, deep-donk. Boopy-doopy-doopy-doop. And I get 5.64 times 10 to the 23rd atoms. That was my calculator sound, by the way. 5.64 times 10 to the 23rd atoms. Okay? Now there's one other conversion factor that we haven't really talked about too much, and that's liters, okay? It turns out, let's say I'm trying to figure out how many moles hydrogen is. Well, hydrogen's a gas, and it's not like I can just dump a balloon full of hydrogen on a balance because it floats. So we have to use volume. And the fun thing is that 22.4 liters of any gas in the world, the universe, any gas in the universe, as long as it's at something called STP, which is standard temperature and pressure. Standard temperature and pressure. Alright? That's essentially sea level. And 0 degrees Celsius. That's standard temperature pressure. Any gas that's at sea level and 0 degrees Celsius, 22.4 liters of it's 1 mole. Does not matter the gas it is. And I think that's pretty cool. Doesn't matter if it is super heavy sulfur hexafluoride or super light hydrogen gas. 22.4 liters of it will be 1 mole. It'll have the identical amount of atoms in it. Might weigh different things because some atoms are heavier than others, but it will have the same number of atoms in it. I think that's a pretty cool fact. Alrighty, well, that was the mole and conversion, so I hope you all had a wonderful time. I hope you are all nice and calm and relaxed. I hope it's not as stressful. I hope you understand it a little bit better than you did in honors chemistry, because this can be a very challenging concept. Alright, have a great rest of your day or evening. Bye.